this lecture of the Fourier transformation. Today I will discuss the properties of the Fourier transformation and then we will solve the questions related to Fourier sine or cosine transform. So let us start with the change of scale property, or first with properties of Fourier transform. First, the linear property. Now suppose that if fx and gx are true function of x, where fx and gx are piecewise continuous and integrable in the interval minus infinity to infinity, then the Fourier transform of this linear equation will be a times the Fourier transformation of x of fx plus b times the Fourier transformation of gx. So this is your linear property, and I think there is no need to prove it because it is very easy. Then change of scale property. Now if Fourier transformation of fx is equal to fs, that means if the Fourier transformation of fx exists, that means the function fx is piecewise continuous and integrable in the interval minus infinity to infinity. Now, if the Fourier transformation of this function is equal to fs, then the Fourier transformation of f of ax is equal to 1 upon a f of s upon a. So let us prove it. The Fourier transformation of a function, let us start with the definition, is equal to minus infinity to infinity ft e to the power ist dt. Now we have to find out the Fourier transformation of f of ax. So let us replace our x by ax, or you can say t by at. So this will be your minus infinity to infinity f of at e to the power ist dt. Let at equal to u, then our dt will be 1 upon a du. So this will be your minus infinity to infinity f of u, and here you can see that our t will be your u by a, so we can write it as this thing, and our dt will be du by a, so we will get 1 by a. Now this is, as you can see that this is the definition of the Fourier transformation of some function fx, and this was your fs. Now here you can see that in place of s, right now we are getting s by a. So that means you can change the variable as our function is fixed. So we can also have u in place, t in place of u. So we will get minus infinity to infinity ft e to the power I s upon a t dt. So that means we are getting s upon a in place of s. So this will be your function of s upon a. So this was your change of scale property. Then shifting property. Okay, before that, therefore, what we have proved? We have proved that Fourier transformation of ax is equal to 1 upon fs upon a. Let us assume a equal to minus 1. Let a equal to minus 1, then we will get the Fourier transformation of f of minus x is equal to, as a is minus 1, so this will be your minus of s. So the Fourier transformation of f of minus x is equal to minus f of minus x, and okay, this is your formula. Now let us prove another formula, which is your shifting formula. So if Fourier transformation of fx is equal to fs, then Fourier transformation of f x minus a is equal to e to the power isa into fs. So let's prove it. So the Fourier transformation of fx is equal to minus infinity to infinity ft e to the power ist dt, and this was your f of s. That means the Fourier transformation of fx is equal to fs. Now as we have to replace our x by x minus s, so let us find its Fourier transformation. So we will get ft minus a e to the power ist into dt. So again, let t minus a equal to u, then we will get dt equal to du, and there will be no change in the limits, so we will get minus infinity to infinity fu e to the power is. Now in place of t we will have u plus a and dt is du. So now from here we can take this isa common. So this is equal to e to the power isa. Then in the bracket we will have minus infinity to infinity fu e to the power isu du. Now in the definite integral we can change the variable. So that means this is your minus infinity to infinity ft e to the power ist dt, and that is your f of s. So you can say that this is your isa into fs. So this is the change of scale property. Then let us prove fourth property, which is your modulation property. So this is your, if Fourier transformation of fx is fs, then the Fourier transformation of fx cos ax is equal to half f of s plus a, and then plus f of s minus a. So let us prove it. The Fourier transformation of fx into cos ax, use our definition, which is your minus infinity to infinity. Then we will have ft in place of ft. Now we will have ft cos at, then e to the power ist, and then dt. So this is the definition of the Fourier transformation. In place of ft we will have ft cos at and then e to the power ist dt. And now this is equal to minus infinity to infinity ft. We can use the definition of the cos theta, which is equal to half e to the power I theta plus e to the power minus I theta, and then we have e to the power ist dt. So this 1 by 2 is common, so we will have ft. Now we can merge these two terms, so this will be your e to the power I s plus a t. Then we will have, in the second term we will have minus infinity to infinity ft e to the power I s minus a t dt. So we will get these two terms. Now this is your minus infinity to infinity ft e to the power I s t dt, and it is the definition of the Fourier transformation. Minus infinity to infinity ft into e to the power I s t dt. Now for ft we have ft, then e to the power I s t. Now in place of s we have s plus a, so this will be your half f of s plus a plus s minus a. So this is the modulation property. Now we have proved the modulation property for the Fourier transformation. We can prove it for the Fourier sine transformation, Fourier cosine transformation. So you can prove the following results, which is your the Fourier cosine transformation of fx into cos ax. The Fourier transformation of fx into cos ax is equal to 1 by 2. Then we will have the sine transformation of s plus a plus the sine transformation of s minus a. This is the first property. Then we can also take its sine transformation. Now the sine transformation, the Fourier sine transformation of this will be half f of s plus a. Then we will have f of s minus a. I think here we will have cosine transformation, so this will be your c. Similarly, we can have two more formulae for your fx sin ax and fx sin ax. We can also find the Fourier transformation, that means Fourier cosine transformation of fx sin ax and Fourier sine transformation of fx sin ax. Let us prove the first part. These two are also a part of the modulation theorem. So let us prove the first part. The Fourier cosine transformation of function, let us write the definition, because the Fourier cosine transformation of a function fx is equal to minus infinity to 0 to infinity, then your function, then into cos, as we are taking the Fourier cosine transformation, so we will have cos st, then your dt. So this is the definition of the Fourier cosine transformation, and we will write it as Fourier cosine transformation of a function. Similarly, for the sine transformation, here we will get sin st. Now let us prove the first part, which is your fx cos ax, and this is equal to 0 to infinity. Now this will be your ft cos at, then cos st dt. Now we can write it as half 0 to infinity ft 2 times cos at into cos st dt. Now we know that 2 cos a cos b. 2 cos a cos b is equal to 2. Let us take this term first. So 2 cos a cos b is equal to cos a plus b so cos s plus a plus cos s minus a, and then we will have t common, plus cos s minus a t, and then dt, because you know that cos a plus cos b will be cos a cos b minus sin a sin b, and here we will get cos a cos b plus sin a sin b. So this is equal to ft cos s plus a t dt. Then for the second term we will have 0 to infinity cos s minus a ft cos s minus a t dt. So now you can see that the first term is here. You can see that this is your f of c. Now in place of s we are getting s plus a. So this will be your half fc s plus a, and this is your fc s minus a. So this is the proof of the first part, and similarly you can prove the second part. So this is the modulation property of the Fourier transformation. Now let us find out some connection between the Fourier transformation and Laplace transformation. So relationship between Fourier transform and Laplace transform. Let's see, is there any relationship between these two transform? For that, let us consider the function ft equal to e to power st into gt, and this is when your t is greater than 0 and 0 for the remaining cases. So let us consider this function, and here let us assume e to power minus st. Let us find out its Fourier transformation. Now the Fourier transformation of this ft will be equal to minus infinity to infinity ft, then we will have e to power ist dt. But as you can see that here the value of the function exists only for t greater than 0. So we can break this limit in two parts, one from minus infinity to 0, and for that our t will be less than 0, and in that case our ft is 0. So our value will exist for only this part, that means when your t is greater than 0. So we can write it from 0 to infinity ft e to power ist dt, because when your t is less than 0 the value of the function was 0. Now for this part our ft is equal to, for this part our ft is equal to e to power minus st into gt, and we have e to power ist dt. So here we can write it as gt. Now we can take t common. So if we take common s and t, then this is equal to, I think there will be your not, please note that this is your xt, not, so this was your xt into gt. This is not your st. So if this is your xt, now here we will have to write it as fx e to power isx or e to power ist dt. Excuse me for a minute. Let us write it as, now here this is your ft e to power ist dt, and it can be written as like this. And for ft, now the value of the ft is e to power minus xt gt. So here we will get, now if we take t common, then in the bracket we will have, if we take our t common, then we will get e to power I. Let us take minus t common, so in the bracket we will have x minus is, and then dt. So we will get this term gt e to power minus t x minus is dt. If we put this term as p, then this is equal to gt e to power minus pt and dt, where our p is equal to x minus is. Okay, now see it. This is your 0 to infinity e to power minus st ft dt, and that is your definition of the Laplace transformation. 0 to infinity e to power minus st ft dt. So this is the definition of the Laplace transformation of a function gt. Therefore, we can see that if the function ft, so we can see that if ft equal to this function e to power minus xt gt, where t is greater than 0 and it is 0 when t is less than 0, then the Fourier transformation of ft is same as the Laplace transformation of gt. So for this function, we have proved that these two are equivalent to each other. Next, let us prove the derivative property. So that means the, I think, fifth property, you can say it is a theorem. So if the Fourier transformation of fx is your fs, that means if the function is piecewise continuous and integrable in the interval minus infinity to infinity, and let us assume the same condition for this f dash, and f dash x is continuous and integrable in minus infinity to infinity, then the Fourier transformation of f dash x is equal to, the Fourier transformation of this is equal to minus is into fs. And if we generalize it, and the generalization of this one is equal to minus is power n into fs. So this is the Fourier transformation of nth derivative of the function fx. Proof, and we will need this formula during our problem related to the partial differential equation. So proof, the Fourier transformation of fx is equal to minus infinity to infinity ft e to power ist then dt. Now let us replace our function by f's derivative, so we will get minus infinity to infinity f dash t e to power ist dt. For this, let us integrate this term because we are getting the differences inside. So the integration of this one will be ft, and then we will have limit from minus infinity to infinity. Then we will have the differentiation of this one will be your minus is, and then we will we will have limits as minus infinity to infinity. Integration of this one will be ft e to power ist dt. Okay, so for the upper limit, when your t tends to infinity, now we will assume that our function is 0. Please note that we will assume that our ft tends to 0 as our x, or you can say t, tends to plus minus infinity. This is the condition. That means ft will be 0 whenever your t tends to plus minus infinity, and you can prove it with the help of the inversion formula, and it holds for the inversion formula. So here you can see that for the upper limit, now if t tends to infinity, then this is 0, and again for the low limit this will be 0 for t tends to minus infinity, and for the low limit we will have e to the minus infinity, and that will be 0 for the low limit. So the first term is 0, and here we will get minus is minus infinity to infinity ft e to the power ist and then dt. So you can say that this is your Fourier transformation of the function fx, and we can write it as f of s. So after one time of this integration, we are getting this result. Similarly, now for the second time, again we can write it as the double derivative will be the Fourier transformation of f dash x, and we can write it as like this. Now if we write this f dash x as gx, then we will get g dash x, where my gx is f dash x. So now using this formula number 1 by 1, the Fourier transformation of some function, the derivative of some function is equal to minus is, then the Fourier transformation of that function, and that means the Fourier transformation of gx. Okay, now gx is f dash x by 1. Now gx is f dash x, so we will get it is as the Fourier transformation of f dash x, and again the Fourier transformation of f dash x is equal to minus is, so we will get the is whole square minus is whole square into f of s. So in general, continuing this process, so if we continue this process, we will get the Fourier transformation of fn x as minus is in power n into fs. So this is the Fourier transformation of nth derivative of a function, and it is equal to minus is whole power n into fs. Next property or next theorem. So if the Fourier transformation of a function fx is fs, that means the function is piecewise continuous and integrable, then the Fourier transformation of xn into fx is equal to minus I power n, then the nth derivative of fs. So this is the nth, this is the Fourier transformation of x power n into fx. So proof, we know that the Fourier transformation of fx is equal to minus infinity to infinity ft e to the power ist dt. So let us replace our function by x power n. Let us replace our function by, okay, we will prove this result with the help of the induction. So the Fourier transformation of, if n equal to 1, then we will have to prove that xn into fx, the Fourier transformation of x into fx is equal to minus I into d by ds of fs. So for n equal to 1, we should have this result. So let us start with the right hand side. And this is a similar result as we have proven in the Laplace transformation, and proof is again similar. So if we start with the right hand side, then we will have minus I into d by ds of fs. Fs means the Fourier transformation. And this is equal to minus infinity to infinity ft e to the power ist dt. Again, use the Leibniz rule of differentiation under integration sign, and which says that this total derivative will become partial derivative. So we will have ft del by del s e to power ist and then dt. So this is equal to minus I, and from here we will get the differentiation of this one will be your I times s, I times t, so we will get minus infinity to infinity ft, and the differentiation of this one with respect to s will be I into t, then e to power ist and dt. So we can write it as I into I will be your, this I into I will be your I square, and I square minus 1, that is plus, so we will get minus infinity to infinity ft t times ft, and then we will have e to power ist dt, and this is your Fourier transformation of t into ft, or you can say x into fx. We can change the variable with this as x. So if we change the variable as x in different integral, we can change our variable if the function is fixed. So we can say that this is the Fourier transformation of x into fx. Therefore, this was your left hand side. Thus we can say that therefore the Fourier transformation of x into fx is equal to minus I into the first derivative of fs. Now continuing the similar process as we have done in the Laplace transformation, we get, in generalizing this process, we will get Fourier transformation of x power n into fx as is minus 1 to power n, then the nth derivative of fs. So this is the Fourier transformation of x power n into fx. Now let us solve some question related to the Fourier sine or cosine transformation. So the first question, find the Fourier cosine sine transformation of e to power minus x, and deduce that this 0 to infinity t into sine tx dt upon 1 plus t square is equal to pi by 2 into e to power minus x, and we have to prove that this is equal to pi by 2 into e to power minus x. Solution. Here we will prove this result with the help of the sine transformation. The sine transformation of a function fx is equal to, the sine transformation of function fx is equal to integral 0 to infinity, then we will have the function, say this is your ft, and then cos, as we are taking the sine transformation, so we will get sine st and then dt. So this is the definition of the sine transformation. Now for ft, we have e to power minus t. So in place of ft, we have e to power minus t. So this is equal to this one. Now we have the direct result of this integral, and the result of this integration was equal to e to power minus t upon 1 plus, that means I am writing the general formula, e to power ax sin bx. So the integration of this was e to power ax upon a square plus b square, then this was your a sin bx minus the differentiation of sin bx, which is your b times cos bx. So this is your formula. Now using this formula, we will get e to power minus t upon 1 plus s square, as we are integrating with respect to t. So 1 upon s square. So now in the bracket we will have, here you can see that our a is minus 1, so this is your minus sin st, and then the differentiation of sin bx, with respect to t. Now the differentiation of sin st with respect to t will be your s cos st. So this is your formula, and then the limits from 0 to infinity. Now if your t equal to infinity, then we will get e to the power minus infinity, which is 0. Now if t is 0, we will get cos 0, which is your 1, and here we will get sin 0, which is your 0. So our answer will be s upon 1 plus s square. So this is the Fourier transformation of the function, Fourier sine transformation of function e to the power minus x. Therefore, the Fourier sine transformation of the function e to the power minus x is equal to s upon s square plus 1. You can take this as a formula. Now, using the inversion formula, the inversion formula was, so the inversion formula of sine transform is equal to 2 upon pi, then 0 to infinity. Now we will use the Fourier. So this is your Fourier sine transformation of this. So here we will get this term, and then e to the power minus I s x, or you can say e to the power ist. Then we will integrate with respect to, then say here x, and then we will integrate this term with respect to s, because we are getting f of x. So now in place of this f, Fourier sine transformation of the function fx, we have s upon s square plus 1. Then we will get e to the power minus isx into ds. Okay, again break this term into real and imaginary part. So we will get cos sx minus I times sin sx into ds. Oh, sorry, here this is not true, because we are finding the inversion formula of the sine transformation. So we will have sin sx and then the integration with respect to ds. So here we have sin sx. Now no need to break it. Therefore, the integral 0 to infinity s into sin sx upon s square plus 1 into ds is equal to pi upon 2 into fx, and our fx was e to the power minus x. Now here we can change our variable. So if we change it as t, then we will get sin tx upon 1 plus t square dt equal to pi upon 2 e to the power minus x, and this